Close your eyes, if they aren't already, and let the room fall away. Just the dark behind your eyelids, and the sound of a voice, and the quiet. There is no test here. There is nothing you need to remember. This is just a slow drift outward, a gentle floating through a question that sounds simple, but opens into something much wider. The question is this: is the sun above or below the galaxy? It sounds like asking whether a house sits uphill or downhill, whether a bird is higher or lower than the tree line. But the moment we step into space, those words, above and below, start to wobble. They lose their grip. Because out there is no ground, no floor, no ceiling, no universal up printed anywhere on the fabric of things. Every above and every below we talk about tonight is a choice, a direction we agree on, measured from something we decide to use as a reference. And the first quiet, soothing thing to let settle in your mind is just that. Space does not come with labels. It does not hand us a compass with north written at the top. We bring the compass, we draw the lines, and from those lines, whole architectures of understanding unfold. So tonight, as you lie here, we're going to float outward through those chosen directions, step by gentle step. We'll start close, right at the sun itself, and ask what its own north and south poles even mean. Then we'll widen the circle, out to the flat plane where the planets roll, and we'll see how the sun's own tilt makes a quiet little angle against the rest of the solar system. From there, we'll pull back farther, much farther, until the whole solar system becomes a single point swimming in the vast flat disk of the Milky Way. And we'll ask where that point sits, relative to the disk's own chosen equator. Is it a little above, a little below? And does it stay there, or does it move, over millions and millions of years, like a slow breath, drawn and released? And then, because the universe builds layers like an onion, we'll step outward once more, to the galaxy's own true poles, fixed points in our night sky that anchor the whole spinning wheel. And finally, in the last stretch of our journey, we'll return close to home, to the bubble the sun blows around itself, the great magnetic balloon we ride through space, and we'll see that it, too, has its own quiet north and south. By the end, we will have traced above and below, from the sun's skin out to the edges of our local cosmic neighborhood, and then we'll simply rest there, floating, with no fixed direction pulling at us. But all of that comes later. Right now, in this opening, the only task is to feel what it means to float. Imagine, if you will, a warm, dark sea. There is no surface above you, glinting with light, and no sandy bottom far below your feet. You are suspended in a temperature so perfectly matched to your own skin that you cannot tell where your body ends and the water begins. There is no current tugging you in any direction, no bubbles drifting upward to betray a surface somewhere overhead. If you let your arms drift out to your sides and your legs hang loose, you will not sink, you will not rise. You will simply be. This is the closest we can come, in our earthbound imaginations, to the feeling of real, unanchored space. Because in space, every direction is the same direction. There is no gravity well large enough or close enough to pull you into a definitive fall. The sun's pull is everywhere, but it's a curved geometry, not a downhill slope. The galaxy's pull is everywhere, but it, too, is a slow orbit, not a plummet. So the very idea of above requires us to first pick a flat reference surface, an equator or a plane, and then decide that one side of that surface is north and the other is south, one side is above and the other is below. Without that choice, the words mean nothing, and we make those choices all the time, without even thinking about them. Here on Earth, above is the direction away from the ground. Below is the direction toward the ground. The planet's gravity gives us a universal reference, and our bodies feel it every second of every day, even when we're lying down with our eyes closed, even when we're half asleep and dreaming. The pressure of the mattress against your back is the earth telling you which way is down. The weight of the blanket is the same message, repeated softly across your skin. But if you were to fall asleep in orbit, in true free fall, that message would vanish. Your inner ear, which normally senses the tug of gravity, would float into confusion. Your arms would drift upward without your permission. The idea of above and below would become something you had to decide consciously, using your eyes, using a chosen reference point, the curve of the Earth outside the window, the orientation of the spacecraft walls. And even then, it would be arbitrary. You could stick a label on the ceiling that says north, and a label on the floor that says south, and your brain would slowly accept it, and you would begin to feel, in your bones, that the ceiling was truly up. But it would be a story you told yourself. A useful story, a necessary story, so you could move and work and sleep without your mind constantly spinning. And all of our cosmic directions tonight are exactly that. Useful stories, necessary orientations, agreed upon fictions that let us map the unmappable. So the first image I want to leave with you, here in this soft opening, is the image of a compass needle floating freely, not pointing anywhere, just drifting in a slow, lazy rotation. There is no magnetic field around it, no north to lock onto. The needle turns and turns, weightless, silent, perfectly indifferent. This is the state we have to gently unlearn before we can learn the rest. We have to let go of the assumption that the universe has a built-in that way, a true upward and a true downward. Because if we carry that assumption with us into the galaxy, we will spend the whole night trying to stand the galaxy on its edge like a giant coin, and we will miss the more beautiful truth, which is that the galaxy is a floating, spinning, slowly breathing collection of stars and dust and dark matter, and we are inside it, and we get to decide, for our own peace of mind, which way we call up. Now, as we settle deeper into this quiet, let's start to give that floating compass needle some context. Let's start to build, very gently, the series of reference surfaces we'll use tonight. The first one, the closest one, is the sun's own equator. The sun spins. It's a huge glowing ball of hot gas, and it turns around an axis, just like Earth does. That axis defines two poles, a north and a south, and a waistline around the middle, an equator. For the sun, above can mean toward the North Pole, and below can mean toward the South Pole. This is our first chosen direction, our first human label stuck onto a star. It's real, in the sense that the sun really does spin, and its axis really does point in a specific direction relative to the rest of the solar system. But it's also just a label. The sun does not know it has a North Pole. No sign hangs there. No flag stands planted. The pole is simply the spot where the spin axis meets the surface, a mathematical point we can calculate and name. From there, we'll widen the circle a little to the flat plane of the planets. Earth and Mars and Jupiter and all the rest orbit the sun in a thin, flat disk, a plane we call the ecliptic. This is our second reference surface. If we treat the ecliptic as a flat tabletop, then above the table and below the table have clear meanings. But here's the gentle twist. The sun's own equator is tilted slightly compared to that tabletop, about 7 degrees of tilt. So the suns above and the solar systems above are not the same direction. They're close, but they're not identical. And that means if you were standing on a planet and pointing up, out of the solar system, your finger would be aimed about 7 degrees away from the sun's own North Pole. A small difference, but a real one. A quiet reminder that every reference surface is a choice, and choices can differ. Then we'll pull back even farther, to the galaxy itself. The Milky Way is another flat disk, vastly larger, made of hundreds of billions of stars, including our own. That disk defines a third reference surface, the galactic plane. And we can ask, quite simply, where our sun sits relative to that plane. Is it a little above the plane, or a little below? This is the core of tonight's question. And the answer, which we will spend a long, slow section exploring, is that the sun is currently a little bit above the midplane of the galaxy, by a distance that is tiny compared to the galaxy's full width, but huge compared to our everyday measures. And it's not fixed there. Over millions of years, the sun bobs up and down, crossing through the plane, rising above, sinking below, in a slow, rhythmic motion that has no urgency at all. It's a breathing motion, a floating motion, a gentle oscillation that carries our whole solar system through the disk, like a leaf rising and falling on a barely perceptible swell. Beyond the galaxy's disk, we'll look at the galaxy's own poles. The whole spinning wheel of the Milky Way has a true north and south, fixed points in our sky that we can point to. The North Galactic Pole lies in the direction of the constellation Coma Berenices, a faint spray of stars near the handle of the Big Dipper. The South Galactic Pole lies in the direction of the constellation Sculptor, a dim grouping far below the celestial equator. These are not physical objects you can touch. They are directions, pure and simple, the axis around which our galaxy turns. And they remind us that even a galaxy, for all its vastness, is just another spinning body, another top set in motion by the combined gravity of its parts, and we can label its poles just as we label the sun's. Then, in the final stretch, we'll come back inward, to the bubble the sun blows around itself. The solar wind, a constant stream of charged particles flowing outward from the sun's outer atmosphere, inflates a vast magnetic balloon called the Heliosphere. This bubble pushes against the thin gas between the stars, and it too has a shape with a north and a south, a front and a back, a whole geography of its own. We are inside that bubble right now, every planet, every moon, every comet, and the bubble is moving with us through the galaxy, carrying us along, while its own internal poles shift and sway with the sun's magnetic moods. And at the very end, we will simply let all these layers settle. The sun's poles, the solar system's plane, the galaxy's disk, the galaxy's poles, the local bubble of hot gas we drift through, the sun's own wind-blown bubble, all these nested aboves and belows, each one a human choice, a reference surface drawn onto the dark. And we will return to that first image, the floating compass needle, the warm dark sea with no floor and no ceiling. And we will rest there, knowing that the universe does not demand we orient ourselves. It simply is. We are the ones who bring the directions, gently, calmly, as a way of feeling at home, in a space that has no edges. So let that be the shape of the night ahead. No rush, no wait, no test. Just a slow outward float through chosen coordinates, a quiet tour of the labels we have stitched onto the sky. If you drift off before we reach the end, that is perfectly fine. The words will keep going, soft and steady, and your mind can pick them up or let them go as it pleases. There is no quiz at the door. There is only the dark and the voice and the slow turning of the great wheel we live inside. Let's begin then, with the closest fire, the one that warms our days and lights our path through the galaxy. Let's start with the sun's own north and south, and what it even means for a star to have poles. The sun is a star. It's easy to forget that, because it looks so different from the tiny points of light that come out at night. It's a disk in our daytime sky, warm and bright, something that feels solid and nearby. But it is a star, a huge sphere of hot, glowing gas, mostly hydrogen and helium, held together by its own gravity. And like many things in space, it spins. It turns around an invisible line that runs through its center, the same way a top spins on a table, the same way a basketball rotates on a player's finger. That invisible line is its axis, and the 2 points where the axis meets the surface are the poles. One we call north, the other south. These are the sun's physical poles, the geographic poles, the poles of its rotation. If you could float above the sun, far enough away that its heat wouldn't touch you, and look down along that axis, you would see the whole star turning beneath you, a slow, steady rotation that never stops. The direction of the spin tells you which pole is which. If the sun spins counterclockwise as you look down at it, you're looking at the North Pole. If it spins clockwise, you're looking at the South Pole. This is the same convention we use on Earth, the same right-hand rule that assigns north and south to any spinning body. And the sun's rotation is, in itself, a quiet, steady fact, something that has been happening for more than 4 billion years, and will continue for billions more. But the sun is not a solid ball like Earth. It's a fluid, a churning ocean of hot plasma, and because it's fluid, it doesn't rotate all at the same speed. This is one of the first gentle surprises about the sun's poles, and it's worth sitting with for a moment. On Earth, the ground beneath your feet rotates as one piece. The bedrock of Canada, the sands of the Sahara, the ice of Antarctica, they all complete one turn in 24 hours, together. The air and the oceans move differently, of course, flowing in currents and winds, but the solid planet itself is a single, rigid rotator. The sun is not like that. The sun is gas all the way through, or more precisely, plasma, a state of matter so hot that electrons are stripped away from their atoms, leaving a soup of charged particles. And this plasma rotates at different speeds depending on how far you are from the equator. Near the sun's equator, the plasma completes one full rotation in about 25 Earth days, but as you move toward the poles, the rotation slows down. At higher latitudes, around the sun's shoulders, a full rotation can take about 30 days, and near the poles themselves, the rotation period stretches out to roughly 35 days. This means the equator is constantly lapping the poles, sliding past them, completing 10 extra rotations in the time the poles manage just 7. This is called differential rotation, a term that simply means the sun spins at different rates depending on latitude. It's not a violent thing. It's a slow, smooth, continuous slipping, a giant sphere of glowing gas, turning in a state of gentle internal shear. And it's because of this differential rotation that the sun has a much more complicated life than a simple, solid spinning ball ever could. That shearing motion, the equator sliding past the slower-moving material above and below it, is one of the main engines of the sun's magnetic activity. The sun's interior is full of charged particles in motion, and moving charged particles generate magnetic fields. As the plasma churns and rotates at different speeds, it twists and tangles those magnetic fields, winding them up like rubber bands stretched too far. Those tangled fields rise through the sun's outer layers, bursting through the visible surface, creating the spots and loops and flares we observe. But we're getting a little ahead of ourselves. The magnetic poles are a separate story, one we'll turn to in the next section. For now, let's stay with the physical poles. The simple spinning axis. The sun's rotation axis is not perfectly upright relative to our view of it. It's tilted. Specifically, it's tilted by about 7¼ degrees compared to the plane of Earth's orbit around the sun. That plane, the flat disk in which our planet travels, is called the ecliptic, and we'll spend much more time with it later. But for now, the key point is that the sun's north pole is not pointing straight up and down as seen from Earth. It's leaning slightly, tipped toward us or away from us depending on the time of year. In early June, the sun's north pole is tipped slightly toward Earth, and we get our best view of the northern reaches of the solar disk. In early December, the south pole tips toward us instead. It's a small tilt, just 7¼ degrees, but it's enough to give us a slightly changing perspective as the months roll by. We are always looking at the sun from within the plane of our own orbit, which means we are always seeing it from near its equator, never from directly above or directly below. The sun's poles are, from our vantage point, always seen at an angle, always foreshortened, always a little mysterious. For most of human history, we had no way to see the sun's poles directly. Every telescope, every camera, every set of human eyes has been stuck in that near equatorial perspective, looking across the sun's waistline rather than down onto its crown. We could infer things about the poles. We could watch how the sun's magnetic field behaved and guess what might be happening up there. But we couldn't see them straight on. It's only in the last few decades that we've managed to send spacecraft out of the ecliptic plane, tilting their orbits so they could fly over the sun's poles and look down at them directly. The first spacecraft to do this was called Ulysses, a joint mission between NASA and the European Space Agency. Ulysses launched in 1990 from the Space Shuttle Discovery, but it didn't head straight for the sun. Instead, it flew out to Jupiter first, using Jupiter's enormous gravity to slingshot itself out of the ecliptic plane and into a polar orbit around the sun. This was a clever piece of navigation. The ecliptic plane is the highway of the solar system, the flat region where all the planets roll. Getting out of that plane takes a lot of energy, more than any rocket could manage on its own. But a gravitational assist from a giant planet like Jupiter could do the job, bending the spacecraft's trajectory upward, out of the plane, into a loop that would carry it over the Sun's north and south poles. From 1994 to 2008, Ulysses made 3 polar passes, 2 over the South Pole and 1 over the North, measuring the solar wind and the magnetic field at high latitudes, giving us our first real taste of what the Sun's poles are like. And what did Ulysses find? It found that the solar wind, the stream of particles flowing outward from the Sun, behaves differently at the poles than it does near the equator. Near the equator, the solar wind is slower and more variable, gusty and changeable. Over the poles, the solar wind is faster and steadier, a smooth, rapid outflow of particles streaming away from the Sun's magnetic poles. We'll come back to the solar wind much later, when we talk about the great bubble it inflates around our solar system. For now, the point is simply that the Sun's poles are real places, distinct regions with their own behavior, their own character, and we have only recently begun to see them clearly. More recently, a spacecraft called Solar Orbiter, another European Space Agency mission with contributions from NASA, has been tilting its orbit to get even better views of the poles. Solar Orbiter launched in 2020, and over the course of its mission, it will gradually incline its orbit to more than 30 degrees out of the ecliptic, allowing it to photograph the Sun's poles with far greater detail than Ulysses ever could. Ulysses carried instruments that measured particles and fields, but it had no camera. Solar Orbiter has cameras, and it is slowly, patiently, building a portrait of the solar poles that we have never had before. The first images from Solar Orbiter have already shown us features near the poles that we didn't expect: small, bright, short-lived flares called campfires, flickering across the surface like sparks from a distant fire. These campfires are tiny by solar standards, but they may help solve a long-standing mystery about why the Sun's outer atmosphere, the corona, is so much hotter than the surface below it. But again, that is a story for another night. For tonight, the quiet thing to hold in your mind is simply this: the Sun has a North Pole and a South Pole, just as Earth does. They are the points where its axis of rotation meets its visible surface. The Sun spins more slowly at those poles than it does at its waist, a gentle differential rotation that shapes so much of the star's behavior. And those poles are tilted slightly relative to our view, leaning toward us for part of the year and away for the rest, always seen at a slant, never fully revealed. We have spent most of our history wondering what they look like. Only now, in this small slice of time, are we beginning to see them face to face. And yet, for all that, the physical poles are only half the story. The Sun has another set of poles, a magnetic set, and those poles do something that Earth's magnetic poles would never do. They trade places, they flip. North becomes south, south becomes north, and then, after another stretch of years, they flip back again. That is where we are going next, into the strange, cyclical life of the Sun's magnetic poles, the ones that cannot sit still. Let the image of the spinning Sun settle in your mind as we pause here. Picture it slowly turning, its equator outspinning its poles, its axis tipped just slightly, a great glowing sphere rotating in the quiet dark, with a north and a south that we have only just begun to know. And as you rest with that image, let it carry you gently toward the next part of our journey, where the poles begin to move and trade places in a rhythm that has been beating for billions of years. The Sun has a second set of poles, and they are not fixed in place like the physical spin poles we just visited. These are the magnetic poles, and they do something that at first hearing sounds impossible. They switch, they trade places. North becomes south, and south becomes north. And then, after a pause, they do it again, back and forth, in a slow, steady rhythm that has been ticking away for most of the Sun's life. To understand what this means, we have to step back for a moment and think about what a magnetic pole actually is. You've probably held a magnet at some point in your life. maybe a small bar magnet, the kind that sticks to a refrigerator door. That magnet has two ends, two faces. One face we call north, the other south. If you bring the north face of one magnet near the south face of another, they pull toward each other, they attract. If you bring two north faces together, they push apart, they repel. This is the basic language of magnetism, the push and pull that governs everything from refrigerator doors to the vast magnetic fields that wrap around entire planets and stars. Earth itself has a magnetic field, generated by the churning of molten iron deep in its core. That field has a north magnetic pole and a south magnetic pole, and they sit fairly close to the geographic north and south poles, the spin poles, though not exactly on top of them. A compass needle points toward Earth's magnetic north pole, which is why compasses work. And Earth's magnetic poles, for the most part, stay put. They wander a little, drifting slowly over the decades, but they don't flip. Not in human timescales anyway. Over geologic time, over millions of years, Earth's magnetic field has flipped many times. North becomes south, south becomes north, and the evidence is written in the rocks of the ocean floor, in the frozen orientation of magnetic minerals that locked in the direction of the field when the lava cooled. But these flips are irregular, spaced hundreds of thousands or even millions of years apart. They are not something that happens on a schedule a human mind can easily hold. The sun is different. The sun's magnetic poles flip on a regular, predictable beat. Roughly every 11 years, the sun's magnetic north pole becomes a magnetic south pole, and its magnetic south pole becomes a magnetic north pole. 11 years later, they flip back. This means the full cycle, from north to south and back to north again, takes about 22 years. This 22-year cycle has a name, the Hale cycle, named after the American astronomer George Ellery Hale, who first worked out the pattern in the early 20th century. The 11-year half of that cycle, the period from one flip to the next, is called the solar cycle, or sometimes the sunspot cycle, because the flipping of the magnetic poles is closely tied to the coming and going of dark spots on the sun's surface. Let's sit with those spots for a moment, because they are the most visible sign of the magnetic drama unfolding above and below. Sunspots are dark patches on the sun's visible surface, the photosphere. They look dark because they are slightly cooler than the surrounding gas. A typical sunspot might be around 4,000 degrees Celsius, while the surrounding photosphere is closer to 5,500 degrees. That temperature difference makes the spots appear dark by contrast, though if you could somehow pluck a sunspot out of the sun and hang it in the night sky, it would still glow brighter than the full moon. Sunspots are places where intense magnetic field lines have pushed up from the sun's interior, punching through the surface and holding the hot plasma in place, preventing it from circulating and cooling the way it normally would. The magnetic field at a sunspot can be thousands of times stronger than Earth's own magnetic field. It's a tangled knot of magnetism made visible, a bruise on the sun's bright face. And sunspots come and go in a rhythm that matches the magnetic pole flip. At the beginning of an 11-year solar cycle, when the sun's magnetic field is at its quietest, sunspots are few and far between. The sun's face is mostly clear, mostly smooth, a blank golden disk. But as the cycle progresses, sunspots begin to appear more frequently, first at higher latitudes, closer to the poles, and then gradually migrating toward the equator. The number of sunspots rises and rises, peaking around the middle of the cycle, a period called solar maximum. At solar maximum, the sun's face can be dotted with dozens of spots at a time, some of them large enough to swallow Earth whole. Then, after the peak, the number of sunspots begins to decline again, falling toward a quiet minimum, a solar minimum. And it's right around that minimum, when the sun's face is at its most blank and peaceful, that the magnetic poles flip. The old north becomes the new south, the old south becomes the new north, and the whole cycle begins again, sunspots and all, but with the magnetic polarity reversed. What does that reversal actually look like? If you could see magnetic fields the way we see light. It's not a single, clean moment. It's not as if the sun has one north pole and one south pole that suddenly swap places on a Tuesday afternoon. The sun's magnetic field is complicated, messy, full of loops and tangles and localized knots. During the flip, the large-scale, organized dipole field, the simple north-south bar magnet shape, breaks down into a more chaotic state. The poles fragment and wander. New magnetic flux bubbles up from below, canceling out the old field and replacing it with fresh field of the opposite orientation. The process can take months, even a year or more, and it doesn't happen at exactly the same time at the north and south poles. One pole might flip before the other, leaving the sun with two temporary north poles or two temporary south poles, a state of magnetic confusion that eventually sorts itself out into a new, stable, reversed dipole. This is one of the things that scientists are still working to understand, the exact sequence of events that takes place deep inside the sun, in the churning convection zone, that leads to this regular, rhythmic reversal. The timing is observed, the pattern is well documented, but the deep internal mechanics, the precise flows and feedbacks that drive the flip, are still debated. The leading idea involves something called the solar dynamo. A dynamo is a machine that turns mechanical energy into electrical and magnetic energy. Inside the sun, the mechanical energy comes from the rotation and the churning convection of the plasma. The differential rotation we talked about in the last section, the equator spinning faster than the poles, winds up the magnetic field lines, stretching them out and wrapping them around the sun's interior. At the same time, the rising and falling of hot plasma, the convection that brings heat from the sun's core to its surface, twists and tangles those field lines further. Together, these motions create a self-sustaining dynamo that generates the sun's entire magnetic field. And within that dynamo, the story goes, there is a kind of memory, a built-in tendency for the field to reverse polarity every 11 years. The exact details of how that memory is stored and how the reversal is triggered are still not fully known. There are computer models that simulate the solar dynamo, and some of them produce flips that look a lot like the real thing. But the models are not yet complete enough to predict the timing and strength of future solar cycles with perfect accuracy. The sun keeps some of its secrets even now. This is a good place to pause and say plainly that not knowing is part of the calm. The fact that we don't fully understand why the sun's magnetic poles flip is not a cause for alarm. It's not a gap we have to rush past. It's a reminder that the sun is a real, physical object, vastly older than us, operating on scales of time and energy that our minds can only approximate. We have been watching the sun with telescopes for only about 400 years, a tiny fraction of its life. In that short time, we have learned an enormous amount. We have mapped the sunspot cycle, measured the magnetic fields, sent spacecraft to fly over the poles. But the sun is not obligated to reveal all its inner workings to us on demand. The not knowing is part of the quiet mystery of it, part of what makes it possible to lie here in the dark and simply marvel at the fact that a star, our star, breathes magnetically every 11 years, and we can watch it happen from 93 million miles away, safe and warm and unhurried. The magnetic flip has consequences that reach all the way to Earth and beyond. During solar maximum, when the sun's magnetic field is most tangled and active, the sun throws off more frequent flares and more massive clouds of charged particles, called coronal mass ejections. These can disrupt satellites, cause auroras, and even affect power grids on the ground. But during solar minimum, when the poles are flipping and the sunspot count is low, the sun is quieter. The solar wind, which we'll spend time with later, changes its character. The heliosphere, the great bubble the sun blows around the solar system, shifts its shape. The magnetic flip is not just a local event on the sun's surface. It's a global reorganization that ripples outward through all the space the sun touches, and we are inside that space, riding along on a planet whose own magnetic field feels the distant echo of the sun's rearrangements. So as you lie here, Let the image of the physical spinning sun from the last section merge with this new image of the magnetic sun. The physical poles are fixed, steady, anchored to the axis of rotation. The magnetic poles are fluid, restless, trading places on a schedule we can set our calendars by. One set of poles stays put, the other set flips. Together they give the sun a kind of layered identity, a spinning body with a restless magnetic heart. And both sets of poles, physical and magnetic, will follow us as we widen our view in the sections to come. Because the sun's tilt, its physical axis, is not perfectly aligned with the flat plane of the planets, and the sun's magnetic poles, which wander and flip, add their own tilt and their own complexity to the shape of the bubble we all live inside. But that is for later. For now, just let the rhythm of the flip settle in your mind. 11 years up, 11 years down, a breathing cycle of magnetism that has been going on since before the Earth was born and will continue long after we are gone. A slow, silent, invisible dance of north and south, trading places in the dark. Now we widen the frame. We've been sitting close to the sun, looking at its spinning surface, its physical poles, its restless magnetic poles. But the sun does not sit alone in space. It has a family. 8 planets, dozens of moons, countless asteroids and comets, and drifting bits of ice and rock, all of them orbiting the sun in a shared, flat arrangement. And that flat arrangement, that thin disk of orbiting bodies, gives us a new reference surface, a new way to define above and below. And here is the quiet thing that makes this worth a whole section. The sun's own equator, the waistline we talked about earlier, is not perfectly aligned with that flat planetary disk. It's tilted, just a little, about 7 degrees. And that small tilt means that above the sun and above the solar system are not the same direction. They point to slightly different patches of sky, and there's no drama in that fact, no urgent implication. It's just a gentle geometric truth, a quiet angle that sits at the heart of our cosmic home, and it's worth sitting with for a while. Let's start with the flat disk itself. If you could float high above the solar system and look down, you would see that all the planets orbit the sun in roughly the same plane. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. They all trace their paths in a thin, flat region, like marbles rolling on an invisible tabletop. This is not a coincidence. It's a relic of how the solar system formed, about 4.5 billion years ago. The whole thing started as a vast, slowly rotating cloud of gas and dust. Gravity pulled that cloud inward, and as it shrank, it spun faster, the way an ice skater spins faster when she pulls her arms in. That spin flattened the cloud into a disk, and it was within that disk that the planets were born, clumping together from the gas and dust that surrounded the young sun. Because they formed within that flat disk, they inherited its flat motion. They all orbit in roughly the same plane, and they all orbit in the same direction, the direction of the original cloud's spin. This is why the solar system looks the way it does. A central star, a flat set of planetary orbits, a tidy, spinning arrangement that has persisted for billions of years. That shared plane has a name. It's called the ecliptic. The word comes from the same root as eclipse, because eclipses happen when the moon crosses this plane at just the right time to fall into Earth's shadow or to block the sun's light. The ecliptic is not a physical thing you can touch. There is no glowing line in space marking it. It's a mathematical plane, a flat surface defined by Earth's orbit around the sun. All the other planets orbit very close to that same plane, though not exactly on it. Mercury's orbit is tilted by about 7 degrees relative to the ecliptic, the most of any planet. Venus is tilted by about 3.5 degrees. The outer planets have tilts of less than 2 degrees, so the solar system is not a perfectly flat pancake. It's more like a stack of very thin plates, each one shifted by a tiny angle, all of them together forming a region that is mostly flat, mostly aligned, but with small, graceful variations. Now, the sun itself, the great glowing center of this whole arrangement, spins on its own axis. And as we learned earlier, that axis is not perfectly perpendicular to the ecliptic. It's tilted by about 7¼ degrees. This means the sun's equator, the imaginary line around its middle, is not lined up with the plane of the planets. There is a small but real angle between them. If you imagine the ecliptic as a flat tabletop, the sun's equator is like a dinner plate resting on that table, but with one edge lifted slightly, tilted by about the thickness of a finger. It's a small angle, but in the vastness of the solar system, small angles matter. Why does this tilt exist? The honest answer is that we don't know for sure. The sun contains most of the mass of the solar system, more than 99% of it. You might expect that the sun's equator would perfectly align with the plane of the planets, since the whole system formed from the same spinning cloud. But it doesn't. The 7-degree tilt is a kind of fossil clue, a hint that the formation of the solar system was not perfectly smooth and symmetrical. Maybe the original cloud had some turbulence, some internal sloshing that left the central star tilted relative to its disk. Maybe a close encounter with another star early in the sun's life tugged its axis slightly askew. Maybe the gravitational influence of the giant planets, Jupiter and Saturn mostly, slowly nudged the sun's axis over billions of years. The tilt is observed, it's well measured, but its origin is still a matter of quiet scientific discussion. And that's fine. Not every tilt needs an urgent explanation. Some angles are just there, a part of the given geometry of our home, and we can simply note them and move on. But this tilt does have a gentle consequence for how we see the sun. As we noted in the first section, the tilt means that we on Earth, orbiting in the ecliptic plane, never see the sun's poles straight on. We are always looking at the sun from near its equator, because our orbit keeps us in that flat plane, and the sun's equator is only slightly tilted relative to us. During part of the year, when Earth is at the right point in its orbit, we can see a little bit more of the sun's north pole, tipped slightly toward us. 6 months later, we see a little bit more of the south pole. It's a subtle effect, a 7-degree nod, but it's real, and it gives the sun a gentle seasonal rhythm from our perspective, a slow tilting back and forth that repeats every year. More importantly for our journey tonight, this tilt means that above the sun and above the solar system are two slightly different directions. If you were standing on the sun's north pole, looking straight up along its axis, you would be looking in a direction that is about 7 degrees away from the direction you'd be looking if you stood on the ecliptic plane and pointed straight up, perpendicular to the orbits of the planets. They're close, but they're not the same. And this means that when we start talking about the sun's position relative to the galaxy, or the shape of the bubble the sun blows around itself, we have to be careful about which above we mean. Are we using the sun's own axis as our reference, or the axis of the solar system, or something else entirely? This is the quiet, cumulative effect of the whole night's journey. Every time we step outward to a larger structure, we find a new reference plane, a new definition of above and below, and each one is tilted slightly relative to the others. The sun's equator is tilted relative to the ecliptic. The ecliptic, as we will see in the next section, is tilted relative to the galaxy's flat disk. The galaxy's disk has its own poles, which point in yet another set of directions. None of these planes are perfectly aligned. They all tilt and lean at gentle angles to one another, a cosmic geometry of quiet misalignment. And that misalignment is not a problem to be solved. It's just the way things are. The universe does not stack neatly. It tilts and leans and drifts, and we are the ones who bring the labels, who decide which plane to call the reference, which direction to call up. Let's take a moment here to simply picture the tilted arrangement we've just described. Imagine the sun, glowing and turning, its axis running from north to south. Now imagine the flat plane of the planets, the ecliptic, spreading out from the sun's middle like a wide, invisible disk. But it's not exactly at the sun's middle. It's tilted slightly, so that the sun's north pole leans about 7 degrees away from the perpendicular. The planets roll around in that tilted plane, following their paths, oblivious to the sun's own internal spin orientation. And here we are on Earth, one of those rolling planets, looking at the sun from within the tilted plane, seeing its poles only at a slant, never straight on. It's a quiet, tilted architecture, a house built on a slight slope, and we've lived in it for all of human history without ever feeling the lean. And now, as we prepare to zoom out much farther, to the galaxy itself, let this tilted image travel with us. Because the solar system's flat plane, the ecliptic, is itself tilted relative to the galaxy, hugely tilted, as it turns out. The ecliptic plane is inclined by about 60 degrees relative to the galactic plane. That's a large angle, more than halfway to perpendicular. So if you picture the galaxy as a vast, flat disk stretching across the sky, our solar system is tilted steeply within it, like a coin resting at an angle inside a much larger plate. And within that tilted solar system, the sun's own equator is tilted by another 7 degrees. Layers of tilt, nested within each other, each one a quiet reminder that above and below are choices, not absolutes. But we're not at the galaxy yet. That's the next section. For now, just let the 7-degree tilt between the sun and its planets settle in your mind. It's a small angle, the kind of angle you might not notice if you weren't looking for it. But it's there, and it's real, and it's the first of several gentle misalignments we will encounter tonight. The sun and its family are not perfectly stacked. They lean against each other, quietly, steadily, like a stack of plates that has settled slightly off-center over the long, slow years. And that lean is part of the quiet beauty of the system, a reminder that even our closest star, the one that lights our days, does not sit perfectly square with the worlds that circle it. Let that tilted image carry you now, softly, toward the next widening of the lens. We've seen the sun's own poles, physical and magnetic. We've seen how the sun's equator tilts against the plane of the planets. Now it's time to step outward, far outward, to the great flat disk of the Milky Way galaxy itself, the vast spinning wheel of stars that contains our sun and 100 billion others, and to begin asking where, within that enormous structure, our little tilted solar system actually sits. Let's take that step slowly. We've been living inside the solar system, picturing the sun and its planets as a kind of local neighborhood, a familiar arrangement of worlds circling a single star. And now we're going to pull back, as if we were rising up and up, watching the solar system shrink beneath us until it becomes a single point of light, indistinguishable from all the other points of light around it. And as we rise, a new shape begins to emerge from the dark. A vast, flat structure, a disk of stars and gas and dust, stretching out across a distance so enormous that our usual measures of miles or kilometers stop being useful, and we have to switch to a different unit entirely, the light year. A light year is the distance light travels in 1 year. Light moves at about 186,000 miles per second, or about 300,000 kilometers per second. In 1 year, that adds up to nearly 6 trillion miles, or about 9.5 trillion kilometers. That's a 1 followed by 12 zeros, a number too large to feel in your bones. But it's the yardstick we need now, because the galaxy is about 100,000 light-years across. That's 100,000 times 6 trillion miles. It's a distance so vast that if you tried to fly across it in a jet plane, it would take you many billions of years, far longer than the age of the universe itself. So we don't fly, we imagine. We picture the whole thing from a comfortable distance, the way you might picture a map of a country you've never visited, letting the shapes and proportions settle in your mind without worrying about the exact walking distance between towns. The Milky Way galaxy, seen from far above, would look like a great spiral of light, a pinwheel of stars with a bright, bulging center and graceful, curving arms. It's a barred spiral galaxy, which means that its central bulge is not a perfect sphere, but an elongated bar of stars, and the spiral arms unwind from the ends of that bar. We know this from decades of careful observation, measuring the positions and motions of stars and gas clouds, building up a map of our own galaxy from the inside. It's not an easy thing to map a galaxy while you're sitting inside it. It's like trying to draw a picture of the entire ocean while you're floating on a raft, with no aerial view. But astronomers have done it, patiently, over many years, and the picture we have now is fairly detailed. We know the galaxy has 4 main spiral arms, or perhaps more, depending on how you count them. We know it has a central bar of stars, and a supermassive black hole at the very center, a dark object weighing about 4 million times the mass of the Sun, around which the whole galaxy turns. And we know that most of the galaxy's visible matter, the stars and the glowing gas clouds, is confined to a thin, flat disk. That flat disk is our next reference plane. Just as the planets orbit in a flat plane around the Sun, the stars of the Milky Way orbit in a flat plane around the galactic center. This plane has a name, the galactic plane. It's the galaxy's own equator, the midline of the great stellar disk. And if we want to ask whether the Sun is above or below the galaxy, this plane is our reference. Above means toward the north side of the disk, away from the plane in one direction. Below means toward the south side, away from the plane in the opposite direction. The galactic plane is not a physical surface. You could fly right through it and never know you'd crossed it. It's a mathematical midline, an average of where all the stars and gas tend to cluster. But it's a useful one, and it gives us a way to orient ourselves within the enormous sprawl of the Milky Way. Now, let's describe the shape of the galaxy in a little more detail, because it's not just a single flat disk and nothing else. The galaxy has layers. The main disk, the one with the spiral arms and the bright young stars and the glowing clouds of gas, is sometimes called the thin disk. It's where most of the action is, where new stars are born, where the spiral arms wind their way outward from the center. This thin disk is, in galactic terms, quite slender. Its thickness is about 1,000 light-years, maybe a bit more, which sounds enormous until you remember that the disk is 100,000 light-years across. The ratio is about 100 to 1. If the galaxy were a pancake, it would be a very thin pancake. If it were a vinyl record, it would be about the right proportions. The thin disk is where our Sun lives, and we'll talk about its exact address in the next section. But above and below that thin disk lies another layer, called the thick disk. The thick disk is a region of older stars, stars that are more spread out, less confined to the exact midline. These stars still orbit in roughly the same plane as the thin disk, but their orbits are a little more tilted, a little more puffed up. The thick disk extends perhaps a few thousand light-years above and below the plane. The stars in the thick disk are generally older than the stars in the thin disk, and they have fewer heavy elements because they formed earlier in the galaxy's history, before many generations of stars had enriched the gas with heavier atoms. If the thin disk is the bright, bustling downtown of the galaxy, the thick disk is the older, quieter neighborhood just outside the center, where things are a little more spread out and a little more calm. And beyond the thick disk, there is yet another layer. The galaxy is surrounded by a vast, roughly spherical region called the halo. The halo is made of very old stars, and also of globular clusters, which are dense, spherical collections of hundreds of thousands of ancient stars bound together by gravity. The halo also contains a great deal of dark matter, the invisible material that makes up most of the galaxy's mass, though we can't see it directly. The halo extends far beyond the disk, out to at least 100,000 light-years from the center, and perhaps much farther. The stars in the halo have random, tilted orbits, not confined to any flat plane. They swarm around the galaxy like bees around a hive, moving in every direction, a faint, diffuse cloud of the oldest stars the galaxy possesses. So when we talk about the galaxy, we're talking about a layered structure, a thin, bright disk of young stars and gas, a thicker disk of older stars above and below it, and a vast spherical halo enveloping the whole thing. And somewhere inside that thin disk, tucked into one of the spiral arms, is a small yellow star with 8 planets, one of which is ours. The Sun is not in the center of the galaxy. It's not in the halo. It's not in the thick disk, though it may drift into the thick disk's lower reaches during parts of its orbit. It's in the thin disk, the main stellar plane, the galaxy's bustling, star-forming heartland, and within that thin disk, It has a specific vertical position relative to the midline. It's either a little bit above the exact midplane or a little bit below. That's the question we'll answer in the next section. But before we get there, let's take a moment to picture what this layered galaxy looks like from the inside. We can't see the galaxy from above because we're stuck inside it, but we can see the disk edge on, stretching across our night sky. On a clear, dark night, far from city lights, you can see the Milky Way as a faint, glowing band of light arching from horizon to horizon. That band is the accumulated light of billions of stars in the thin disk, seen from our position within it. If you look toward the constellation Sagittarius, you're looking toward the galactic center, and the band of the Milky Way is brightest and widest there. If you look in the opposite direction, toward the constellation Auriga, you're looking outward, toward the galaxy's edge, and the band is fainter and thinner. And if you look perpendicular to the band, straight up out of the disk, you're looking toward the galactic poles, where there are relatively few stars, and the sky is darker and emptier. The Milky Way in the night sky is the galaxy's disk seen from within, a visual reminder that we are embedded in a vast, flat structure, looking out through its thickness. And the solar system, as we noted at the end of the last section, is tilted relative to that disk. The ecliptic plane, the flat plane of the planets, is inclined by about 60 degrees relative to the galactic plane. That's a large tilt. It means that the nice, orderly, flat arrangement of our solar system is cocked at a steep angle relative to the galaxy's own flat arrangement. If you picture the galaxy as a vast, horizontal plate, our solar system is a smaller plate, balanced on its edge, tilted about 60 degrees from horizontal. This is why the Milky Way in our sky does not follow the same path as the planets. The planets move along the ecliptic, which is a line that circles the sky at a 60-degree angle to the galactic plane. The Milky Way band crosses the ecliptic at a steep slant, two great circles intersecting on the celestial sphere. This tilt is another one of those quiet geometric facts, a misalignment between our local reference plane and the galaxy's reference plane, and it adds another layer to the question of above and below. Because now we have three different norths: the Sun's North Pole, the Solar System's North Pole, and the galaxy's North Pole. They all point in different directions, and we get to choose which one we mean. But for the purposes of our main question tonight, is the Sun above or below the galaxy? We use the galaxy's own reference plane. We ask where the Sun sits relative to the galactic plane, the midline of the thin disk. And that question, as we'll see, has an answer, though not a perfectly precise one. The Sun is slightly above the plane, by a distance that is small compared to the galaxy's size, but large compared to our everyday experience. And it doesn't sit still, it moves. It bobs up and down, crossing through the plane every 30 million years or so, in a slow, gentle rhythm that has been going on for billions of years. But that's the next section, and the one after that. For now, just let the image of the galaxy itself settle in your mind. A vast, spinning disk of stars, 100,000 light-years across, with a bright center and graceful spiral arms. A thin, flat disk where new stars are born, a thicker disk of older stars above and below it, and a spherical halo of ancient clusters and dark matter surrounding the whole thing. And somewhere in that thin disk, in a spiral arm called the Orion Arm, a little more than halfway out from the center, there is a small yellow star. Our Sun, quietly, steadily, taking its place in the great galactic structure, and we are going to find out exactly where that place is relative to the galaxy's midline in the next quiet stretch of our journey. So here we are, at the heart of the question that gives this whole night its title. Is the Sun above or below the galaxy? We've built up the reference planes, layer by layer. We started with the Sun's own equator, then the solar system's ecliptic plane, and then, in the last section, we pulled back to see the galaxy's own flat disk, the galactic plane. That galactic plane is our reference now. It's the midline of the thin disk, the average height of all the stars and gas that make up the Milky Way's bright, flat body. And the question is simple. Relative to that midline, where is the Sun? Is it exactly on the plane, right in the middle? Is it a little bit above, toward the north side, or a little bit below, toward the south side? The answer, as best as we can measure it, is that the Sun is currently a little bit above the plane. It sits slightly north of the galactic midplane. But the moment we say that, we have to slow down and talk about what a little bit means, and why the exact number is not something we can pin down with perfect confidence. Because this is one of those places where the real science carries genuine uncertainty, and the uncertainty itself is part of the quiet calm of the night sky. We don't have to know everything to appreciate where we are. The not knowing is not a hole to fill. It's just part of the landscape. Let's start with what is generally agreed upon. Most measurements, using a variety of methods, place the Sun somewhere in the range of about 20 to 70 light-years above the galactic plane. That's a range, not a single number, and the fact that the range exists is worth sitting with. Different research teams, using different sets of stars as their reference points, get slightly different answers. Some studies, looking at certain types of young, bright stars that tend to cluster very close to the plane, find that the Sun is about 20 to 30 light-years north of the midline. Other studies, using older stars or different statistical techniques, suggest a height closer to 50 or 60 light-years. A few analyses push the number up towards 70 light-years or even a bit higher. The spread is real, and it reflects the genuine difficulty of measuring our own position within a structure that we cannot see from the outside. Think about what it means to measure the Sun's height above the galactic plane. We are sitting inside the disk, trying to figure out where the midline is by looking at the stars around us. The midline is not a visible line, it's a statistical concept, the average vertical position of all the material in the thin disk. To find it, astronomers have to survey large numbers of stars, measure their distances and their vertical positions, and then fit a plane through the distribution. But different types of stars have different distributions. Young, massive stars are born very close to the plane and haven't had time to drift far from it, so they trace the midline tightly. Older stars have had time to wander, to be nudged by gravitational encounters, to spread out into a thicker distribution. So depending on which stars you use as your reference, you might get a slightly different answer for where the exact midline falls. And then you have to measure the Sun's position relative to that midline, which requires knowing our own distance from all those reference stars with good precision. Every measurement carries some uncertainty, and the uncertainties add up. There's also the question of what exactly we mean by the Sun's position. The Sun is not a point. It's a sphere about 864,000 miles across. But compared to the scales we're talking about now, that size is vanishingly small. 20 light-years is about 120 trillion miles, a distance so vast that the Sun's own diameter is a rounding error. So when we talk about the Sun's height above the plane, we're talking about the position of its center, the point around which all the planets orbit. And that point, as best we can tell, is currently a little bit north of the galaxy's midline. But let's step back from the numbers for a moment and just feel the scale. 20 light-years, 70 light-years. Even the larger of those figures is tiny compared to the overall size of the galaxy. The thin disk, as we noted in the last section, is about 1,000 light-years thick. So if the Sun is 20 to 70 light-years above the exact midplane, it's still well within the thin disk. It's not floating out in the thick disk or the halo. It's comfortably inside the main stellar layer, the region where most of the galaxy's young stars and gas clouds reside. Compared to the full thickness of the disk, the Sun's offset from the midline is small. It's like being a few steps off the center line of a wide road. You're not on the shoulder, you're not in the ditch, you're just slightly to one side of the exact middle. Here's a comparison that might help it settle. Imagine the galaxy's thin disk as a coin, a typical coin like a quarter or a penny. The disk is about 1,000 light-years thick in the region where we live, and the Sun's offset from the midline is somewhere around 20 to 70 light-years. If we take the thickness of the disk as the thickness of the coin, which is roughly 1 or 2 millimeters, then the Sun's offset from the exact center would be about the width of a human hair. A hair's width off dead center. That's how close we are to the midline, in proportional terms. We are, for all practical purposes, riding right in the middle of the galaxy's disk, with only the slightest lean toward the north side. But the coin comparison, while helpful, flattens something important. The galaxy is not a solid coin. It's a collection of stars and gas, all moving, all orbiting, all interacting gravitationally. The midline we're measuring is not a fixed structure. It's a dynamic, evolving reference, and the sun is moving relative to it. The sun's position above the plane is not permanent. It's a snapshot, a single frame in a very long movie. Right now, in this moment of cosmic time, we happen to be a little bit north of the midline. In the past, we were elsewhere. In the future, we will be elsewhere still. The sun bobs up and down through the disk in a slow, rhythmic motion, which we'll explore in the next section. So the number we're quoting, 20 to 70 light-years north, is just our current coordinate, our present address in the vertical dimension of the galaxy. It's not our permanent home. It's just where we find ourselves tonight. And that's a calming thought, in its own way. The sun is not fixed. It's not bolted to a particular spot in the galaxy. It's drifting, slowly, gently, through the disk, carrying us with it. The above we are measuring is a temporary above, a passing phase in a long, slow journey that has been underway for billions of years. If you could come back in 10 million years and measure again, you'd get a different number. You might even find the sun below the plane, on the south side, having crossed through the midline and drifted out the other side. The question, is the sun above or below the galaxy, has an answer, but it's an answer that changes over time, like the tide, like the seasons, like the slow breathing of a sleeping world. Let's also place the sun's horizontal position in the galaxy, just to complete the picture, even though our main question is about the vertical. The sun is not at the center of the galaxy. It's out in the disk, about 26,000 light-years from the galactic center. That's a little more than halfway out from the center to the edge of the visible disk. The sun orbits the galactic center at that distance, completing one full lap every 220 to 250 million years, a period we'll explore more fully in a later section. And it's currently located in a spiral arm called the Orion Arm, or sometimes the Orion Spur, a smaller branch off one of the galaxy's main spiral arms. So our full galactic address might read something like this: Orion Arm, thin disk, roughly 26,000 light-years from the center, and currently about 20 to 70 light-years north of the galactic midplane. It's a long address, but it's ours, and it's the only one we've ever known. The uncertainty in the vertical position, that 20 to 70 light-year range, is worth returning to one more time before we move on. It's a reminder that astronomy is not a collection of perfectly known facts. It's a living, breathing process of measurement and refinement. The numbers we have are the best we can do with the tools and techniques available to us right now. In the coming years, with better surveys of the stars around us, with more precise distance measurements from missions like Gaia, which is mapping the positions and motions of over 1 billion stars in our galaxy, the uncertainty will probably shrink. We may eventually be able to say with more confidence exactly where the sun sits relative to the plane, but for now, the range is part of the honest answer. We know we're north of the plane, but we can't say exactly how far north. And that's fine. It's enough to know that we're close to the middle, riding near the heart of the thin disk, in the thick of the galaxy's stellar population, with the bright band of the Milky Way stretching around us in all directions. So as you lie here, let the image settle of our sun, our little yellow star, floating just a hair's width above the exact midline of a vast spinning disk of stars. Picture the disk stretching out around us, 100,000 light-years across, full of bright young stars and glowing gas clouds and dark lanes of dust. And picture us, a tiny point of light, slightly offset from the center, drifting quietly through the disk on a path that will carry us up and down, over millions and millions of years. We are not lost. We are not adrift. We are exactly where we are, in a galaxy that holds us gently in its gravitational embrace, and we are moving, always moving, in a slow dance that we are only beginning to understand. And that motion, that gentle bobbing through the disk, is where we're going next. The sun does not sit still. It rises and falls like a slow breath through the plane of the galaxy, and that rhythm has been beating since before the Earth was born. In the last section, we placed the sun at its current vertical address, somewhere about 20 to 70 light-years north of the galactic midplane. But that address is only true for this moment, this tiny slice of cosmic time. If you could fast forward or rewind the clock by millions of years, you would see the sun's position change. It would drift upward, away from the plane, then slow, then turn and drift back down, passing through the midline, continuing out the other side, and then slowing again, turning again, in a cycle that repeats over and over. The sun bobs, it oscillates, it rises above the plane and sinks below it, like a buoy on a very slow, very long swell, like a leaf riding a barely perceptible wave. This motion is not random. It's a natural consequence of gravity, of the way the mass of the galaxy is distributed. The galaxy's thin disk is full of stars, gas, and dust, and all of that material exerts a gravitational pull. If a star is exactly in the midplane, the gravitational pull from above and below is balanced. The star feels an equal tug from the mass above it and the mass below it, and it has no reason to move vertically. But if a star is displaced from the midplane, even by a little bit, the balance breaks. If the star is above the plane, there is more disk material below it than above it. The greater mass below pulls the star downward, back toward the midline, and so the star begins to fall, accelerating toward the plane. By the time it reaches the midplane, it's moving at its fastest vertical speed. It shoots through the midline, and now it finds itself below the plane, with more mass above it than below. The gravitational pull reverses, slowing the star's downward motion, eventually stopping it, and then pulling it back upward toward the plane again. And so the cycle continues. The star becomes a kind of pendulum, swinging back and forth through the disk, not on a string, but on the invisible threads of gravity. This is the basic physics of the sun's vertical motion. It's the same physics that governs a weight bouncing on a spring, or a child swinging on a playground swing. The sun is caught in the gravitational well of the galactic disk, and it oscillates within that well, rising and falling, in a motion that has been underway since the sun formed, more than 4.5 billion years ago. Now let's talk about the numbers, because they give a sense of the scale of this motion, even though the numbers themselves carry the same kind of uncertainty we discussed in the previous section. The full up and down cycle, from the highest point above the plane, down through the midline, to the lowest point below, and back up to the starting point, is estimated to take roughly 30 million years. Some studies suggest a slightly shorter period, closer to 25 million years. Others suggest a slightly longer period, perhaps 35 or even 40 million years. The range reflects the genuine difficulty of measuring the exact distribution of mass in the galactic disk, which is what determines the strength of the gravitational pull, and thus the period of the oscillation. The disk is not a uniform slab. It has clumps and gaps, spiral arms and voids, and the sun's path through it is not a perfect, smooth sine wave. It's a complex trajectory through a lumpy gravitational landscape, and different models of that landscape yield slightly different periods. But 30 million years is a good round number to hold in your mind. 30 million years for one complete bob, up and down and back again. To put that in perspective, 30 million years ago, the Earth had no ice caps. The continents were in different positions. The age of the dinosaurs was still tens of millions of years in the future. The first primitive whales had not yet entered the oceans. And that entire span of time, from then to now, is just one vertical cycle of the sun's motion through the galaxy. The sun has completed this bob many, many times over its lifetime. If the sun is about 4.5 billion years old, and each cycle takes roughly 30 million years, then the sun has completed somewhere around 150 of these vertical oscillations since it was born. 150 slow breaths, 150 gentle rises and falls through the plane of the Milky Way. The other number that matters is the amplitude of the oscillation. How far above and below the plane does the sun swing? This is the height of the bob, the peak of the wave. And here, again, the numbers are not perfectly pinned down. Different studies, using different methods and different assumptions about the galaxy's mass distribution, arrive at different estimates. The range generally falls between about 100 and 300 light-years. That is, at the highest point in its cycle, the sun might be as much as 300 light-years above the plane, or as little as 100 light-years, depending on whose model you consult. This is a significant distance. Remember, the thin disk of the galaxy is only about 1,000 light-years thick in total. So at the peak of its oscillation, the sun might be riding near the upper edge of the thin disk, poking into the lower reaches of the thick disk, the region of older, more scattered stars. And then, 30 million years later, it might be near the lower edge, swinging through the thick disk on the other side. But right now, as we noted in the last section, the sun is only about 20 to 70 light-years above the plane. That's well within the range of the oscillation. It means we are currently somewhere in the middle of our vertical journey, not at the peak, not at the trough, just drifting along, rising slowly toward the next crest or falling slowly toward the next crossing. The sun's vertical speed, measured relative to the galactic plane, is only about 7 kilometers per second, or roughly 4 miles per second. That's fast by everyday standards, but on the scale of the galaxy, it's a gentle stroll. At that speed, it takes millions of years to move a distance of 100 light-years. The motion is real, but it is not hurried. It is a slow, patient drifting, a quiet migration through the disk, with no destination and no deadline. And as the sun bobs up and down, it carries everything with it. The planets, the moons, the asteroids, the comets, all of us, the whole solar system, rise and fall together. We are all passengers on this slow vertical train, and we don't feel a thing. There's no lurch, no acceleration pushing us back in our seats. The gravitational field of the galaxy is so smooth, and the motion is so gradual, that we are completely unaware of it. The sun's bobbing is something we can only detect by carefully measuring the motions of other stars and comparing them to our own. It's a motion that exists on a timescale so far beyond a human lifespan that it might as well be a permanent feature of the landscape. But it's not permanent. It's a cycle, a rhythm, a slow breathing of our star through the body of the galaxy. Now, there is one more layer to this story, a layer that some researchers have explored with caution and care. And it's worth mentioning here, not because it's a proven fact, but because it sits at the edge of what we know, and the not knowing is part of the calm. The question is whether the sun's vertical bobbing, and particularly the moments when it crosses through the dense midplane of the galaxy, might have any connection to events here on Earth. The galactic midplane is where the disk is thickest with stars, gas, and dust. It's where the spiral arms are most concentrated. When the sun passes through the midplane, it encounters a denser environment. There are more gravitational nudges from passing stars. There is more interstellar gas and dust. Some researchers have wondered whether these periodic crossings, every 15 million years or so for a half cycle, might correlate with patterns in Earth's geological or biological history. In particular, there have been studies looking at whether the spacing of certain past extinction events, times when a significant fraction of life on Earth died out, lines up with the estimated period of the sun's disk crossings. This is a speculative idea. It is not a settled finding. The evidence is mixed, and many scientists remain unconvinced. The challenges are significant. The dates of past extinction events are not known with perfect precision. The period of the sun's vertical oscillation is not known with perfect precision. Trying to line up two uncertain timelines and declare a correlation is a tricky business, and there are many other possible explanations for extinction patterns, including volcanic activity, asteroid impacts, and long-term climate cycles driven by Earth's own orbital variations. So the link between the sun's galactic bobbing and life on Earth remains, At this point, an intriguing possibility, not an established fact. And it's important to say that plainly, without dressing it up as more than it is. The calm of the night sky does not depend on this connection being true. The bobbing itself, the slow, rhythmic rise and fall of our whole solar system through the galaxy, is beautiful enough on its own. It doesn't need to be tied to anything dramatic. It's just what the sun does. It's how it moves through the gravitational landscape of its home galaxy. It's a motion we share, quietly, without ever feeling a thing. So as you lie here, let the image of this slow bobbing replace the static picture of the sun's position. Don't think of the sun as fixed at 20 to 70 light-years above the plane. Think of it as a point on a wave, a point that is always moving, always drifting upward or downward, tracing a gentle arc through the disk. Imagine the sun rising slowly toward the upper reaches of the thin disk, then pausing, turning, and beginning the long drift back down. Imagine it passing through the midplane, through the densest region of stars and gas, and then continuing out the other side, toward the lower edge of the disk, and then turning again and rising again, and so on, over and over, 150 times since its birth, with countless more cycles to come. It's a motion without urgency, a rhythm without a conductor, a slow, silent dance that carries us all through the galaxy, up and down, like a breath drawn and released over 30 million years. And all the while, even as the sun bobs up and down, it is also moving forward, orbiting the galactic center in a vast circular path. The vertical bobbing is just one component of the sun's motion. The other component is its great orbital journey around the entire galaxy, a journey that takes more than 200 million years to complete. That is the next part of our story, the largest and slowest motion of all, the one full trip around the galactic center that the sun has made only 18 or 20 times in its entire life. And it's to that journey that we now turn, drifting gently from the vertical to the horizontal, from the bobbing to the orbit, from the rise and fall to the long, slow curve around the center of all things. We've been talking about the sun's vertical motion, its gentle bobbing up and down through the galactic disk. But that bobbing is only half the story. While the sun rises and falls, it is also moving forward, tracing a vast, nearly circular path around the center of the Milky Way. This is the sun's galactic orbit, its grand journey around the gravitational heart of our galaxy, and it is, by any human measure, almost impossibly slow and impossibly large. Let's start with what the sun is orbiting. At the very center of the Milky Way, hidden deep within the bright bulge of stars, lies a supermassive black hole. Astronomers call it Sagittarius A star, pronounced Sagittarius A star, a name that simply labels its position in the constellation Sagittarius. This black hole has a mass of about 4 million suns, all packed into a region smaller than the orbit of Mercury. Its gravity is immense, but it is not the only thing holding the galaxy together. The galaxy is not like the solar system, where the sun's gravity dominates and the planets trace simple elliptical paths around it. In a galaxy, the mass is spread out. The central black hole is a tiny fraction of the total. The rest of the mass is in the stars, the gas, the dust, and especially the dark matter, that invisible material that makes up most of the galaxy's heft and extends far beyond the visible disk. The sun orbits the combined gravitational pull of all that mass, everything that lies inside its orbital path. And because the mass is distributed in a large, roughly spherical shape, the sun's orbit is not a simple ellipse, it's a more complex curve, though at our distance from the center, it's close enough to a circle to picture it that way for now. The sun's distance from the galactic center is about 26,000 light-years. That's the radius of its orbit. To travel around a circle of that radius once, the sun must cover a distance equal to the circumference, which is 2 times pi times the radius, or about 160,000 light-years. A light-year, remember, is the distance light travels in a year, about 6 trillion miles. So the total distance the sun covers in one full orbit is something close to 1 billion trillion miles. That's a number with 18 zeros after it. There's no point in trying to feel that distance in your body. It's too large. But we can hold it in our minds as a concept, a vast loop through space that the sun has been following for its entire existence. And how long does it take to complete that loop? Current estimates place the sun's orbital period, the length of one full trip around the galactic center, at roughly 220 to 250 million years. This is sometimes called a galactic year, or a cosmic year. It's a unit of time so large that it makes the entire history of human civilization look like the blink of an eye. 250 million years ago, the continents of Earth were assembled into a single supercontinent called Pangaea. The first dinosaurs were just beginning to appear. The ancestors of mammals were small, shrew-like creatures scurrying through the undergrowth. And the sun was on the opposite side of the galaxy from where it is now, completing the previous lap of its endless orbital journey. The sun's speed along this orbit is, by everyday standards, astonishing. It moves at roughly 230 kilometers per second around the galactic center. Let's put that in a more familiar unit. 230 kilometers per second is about 143 miles every second. In the time it took you to hear that sentence, the sun carried you and the entire solar system about 1,000 miles through space. In an hour, we travel more than 500,000 miles. In a day, more than 12 million miles. And yet, because the orbit is so vast, this breakneck speed translates into a journey so slow that it takes 250 million years to complete. That's the paradox of the galactic orbit. We are moving faster than any human-made object has ever traveled, and yet the trip is so long that the sun has only completed somewhere around 18 to 20 laps in its entire 4.5 billion year lifetime. Think about that number for a moment. 18 to 20 laps. The sun is not old, in galactic terms. It's middle-aged, perhaps. It has orbited the galaxy fewer than 24 times since it formed. If the sun were a person, and one galactic orbit were a year, the sun would be a young adult, just setting out in life. The dinosaurs appeared about 1 galactic year ago. The first life on Earth emerged maybe 12 or 13 galactic years ago. The galaxy itself, which is nearly as old as the universe at about 13 billion years, has completed something like 50 or 60 rotations in its lifetime. Though the number is fuzzy, because the galaxy has grown and changed over time, and its rotation rate has not been constant. The point is simply this. On the grandest scale we can comprehend, the sun is a relatively new arrival, still making its early circuits, still tracing its patient loop through the spiral arms. And as the sun orbits, it does not orbit alone. It carries everything with it. The planets, the moons, the asteroids, the comets, the Kuiper Belt objects, the Oort cloud, all of it moves together, a whole system in motion, bound by the sun's gravity and carried along by the galaxies. We are passengers on this journey, and we have been for our entire existence. Every human who ever lived, every creature that ever crawled or swam or flew, every tree that ever grew, lived its entire life on a planet that was hurtling through space at 143 miles per second, and none of them ever felt a thing. The motion is too smooth, too constant, too much a part of the background fabric of our existence. We don't feel it because everything around us is moving at the same speed in the same direction. It's like being on an airplane flying at a steady cruising altitude. If you close your eyes and the ride is smooth, you might not even know you're moving. The sun's galactic orbit is the smoothest ride in the universe, a 500 million mile per day cruise that has been underway for 4.5 billion years, with no turbulence, no stops, no delays. But the orbit is not perfectly smooth. The galaxy is not a uniform, featureless disk. It has spiral arms, regions of higher density where stars and gas are packed more closely together. These spiral arms are not solid structures. They're more like traffic jams, places where stars slow down as they pass through, bunching up before eventually moving on. The sun, in its orbit, passes through these spiral arms from time to time. The timing of these passages is not perfectly known, but estimates suggest that the Sun crosses a major spiral arm roughly every 100 million years or so. When it does, the environment around the solar system changes. The density of interstellar gas goes up. The number of nearby stars increases. The gravitational nudges become more frequent. Some researchers have wondered whether these spiral arm crossings might have left traces in Earth's geological record, perhaps in the form of increased comet impacts or climate shifts. But as with the vertical bobbing and extinction patterns we discussed earlier, this idea is speculative. The evidence is suggestive but not conclusive. The galaxy is complicated, and teasing out a single cause for events that happened tens or hundreds of millions of years ago is extremely difficult. So we hold these ideas lightly. They are interesting possibilities, not established facts, and the calm of the night sky does not depend on them. What we can say with more confidence is that the Sun's orbit is not a closed circle. The galaxy is not a static structure. It evolves. Stars are born and die. Gas clouds collide and form new stars. The spiral arms wind and unwind. The Sun's orbit has likely changed over time, drifting slightly inward or outward, becoming more or less circular, responding to the shifting gravitational landscape of the galaxy. Some studies suggest that the Sun may have formed a little closer to the galactic center than it is now, and migrated outward over billions of years. Other studies suggest it may have formed farther out and migrated inward. The details are still being worked out, and the uncertainty is part of the quiet mystery of our own origins. We don't yet know the full story of how we got to where we are. We only know that we are here, now, on a planet orbiting a star that orbits a black hole, in a galaxy that has been spinning for most of the age of the universe. Let's try to picture the Sun's orbit in a way that includes the vertical bobbing from the last section. The Sun does not trace a flat, perfect circle in the plane of the galaxy. It bobs up and down while it orbits. The combined motion is a kind of gentle wave, a spiral in 3 dimensions. If you could watch a time-lapse of the Sun's path over 1 billion years, sped up so that a galactic year took only a few seconds, you would see a point of light tracing a wavy circle around the galactic center, rising above the plane, dipping below, rising again, all while sweeping forward on its vast orbital arc. It would look like a firefly caught in a slow, looping dance, or a leaf spiraling in a very wide, very lazy whirlpool. The two motions together, the orbit and the bob, give the Sun its full galactic trajectory, a complex but rhythmic path through the disk. And here's a quiet thought to hold as you rest. The Sun is not the only star making this journey. Every star in the galaxy is orbiting, bobbing, tracing its own path through the disk. 100 billion stars, each one on its own orbit, each one moving at its own speed and in its own direction, all bound together by the shared gravity of the whole. The galaxy is not a rigid object, it's a swarm, a fluid collection of individual stars, each one following the laws of physics, each one tracing a path determined by the total mass of everything around it. And yet, out of all that complexity, order emerges. The disk holds its shape. The spiral arms persist. The galaxy continues to turn, and we continue to turn with it. One small voice in a chorus of 100 billion, all singing the same slow song. So as you drift now, let the image of the Sun's great orbit settle over you. Picture the vast, dark circle of our path around the galactic center, a journey so long that the Sun has completed it fewer than 20 times since it was born. Picture us moving at 143 miles every second, a speed so great it would circle the Earth in under 3 minutes, and yet so smooth we feel nothing at all. And picture the Sun, our small yellow star, carrying us all on its long, slow curve through the spiral arms, bobbing gently as it goes, like a boat on a calm sea, with no destination but the next lap and the next and the next, for billions of years to come. And now, having traced the Sun's full motion, both vertical and horizontal, we are ready to turn our attention to the galaxy's own poles, the fixed directions that anchor this whole spinning structure. the true north and south of the Milky Way itself. We began this journey with the sun's poles, those two quiet points where its spin axis meets its glowing surface. Then we widened out to the solar system's flat plane, and then to the galaxy's vast disk. We placed the sun within that disk, a little above the midline, bobbing gently as it orbits. And now we complete the picture by naming the poles of the galaxy itself. Because just as the sun has a north and south, and just as Earth has a north and south, the entire Milky Way has two poles, two fixed directions that point straight out of the flat disk, perpendicular to the galactic plane. These are the galactic poles, and they are as real and as mappable as any other direction in the sky. Let's start by remembering what a pole is in this context. A spinning object, any spinning object, has an axis of rotation. That axis is an imaginary line running through the center of the object, around which everything turns. The 2 points where that axis intersects the surface, or in the case of a galaxy, where it intersects the celestial sphere, are the poles. For Earth, the axis runs from the North Pole to the South Pole, and the planet spins around it once every 24 hours. For the Sun, the axis runs from its North Pole to its South Pole, and the star spins around it once every 25 to 35 days, depending on latitude. For the Milky Way galaxy, the axis runs from the North Galactic Pole to the South Galactic Pole, and the whole galaxy spins around it, though at our distance from the center, one full rotation takes about 220 to 250 million years. The galactic poles are the points where the galaxy's spin axis meets the sky. They are the ultimate above and below for the entire Milky Way system. Now, because we are inside the galaxy, we cannot see the galactic poles as physical objects. They are not stars. They are not glowing clouds. They are directions, pure and simple, points on the celestial sphere that we can locate with coordinates. If you could fly straight up, perpendicular to the galaxy's flat disk, traveling for thousands of light years, you would eventually find yourself looking down at the Milky Way from above, seeing its spiral arms spread out beneath you like a great pinwheel. That direction, the direction you traveled, is the direction of the North Galactic Pole, and if you turned around and flew the opposite way, straight down through the disk and out the other side, you would eventually see the galaxy from below, and that direction is the South Galactic Pole. These directions are fixed. They don't change. They are the anchor points of the galactic coordinate system, the reference frame astronomers use to map the positions and motions of stars and gas within our galaxy. And here is where it becomes wonderfully concrete. The North Galactic Pole points toward a specific constellation. A constellation is simply a patch of the sky, a region defined by a particular pattern of stars, and the North Galactic Pole lies in the constellation Coma Berenices. That name, Coma Berenices, means Berenice's hair, and it refers to a small, faint constellation tucked between the more familiar patterns of Leo the Lion and Botis the Herdsman, near the handle of the Big Dipper. It's not a bright or famous constellation. You might never have noticed it, but it's there, a soft spray of faint stars, and somewhere in that patch of sky, straight up out of the galaxy's disk, lies the North Pole of the Milky Way. The South Galactic Pole points toward the constellation Sculptor. Sculptor is a dim, southern constellation, far below the celestial equator, not visible from most northern latitudes. It was named in the 18th century by the French astronomer Nicolas Louis de Lacaille, who filled in the southern sky with constellations representing tools and instruments of the arts and sciences. Sculptor is not a bright or flashy constellation either. It's a quiet, unassuming region of the sky. And within it, if you trace the galactic axis downward, you find the south pole of the Milky Way, the point directly opposite Coma Berenices on the celestial sphere. These 2 points, Coma Berenices and Sculptor, are opposite each other. They are the antipodes of the galactic sphere. If you were to draw a line from the North Galactic Pole, through the center of the galaxy, and out the other side, you would hit the South Galactic Pole. They are the fixed ends of the galaxy's spin axis, the 2 points around which the great wheel of the Milky Way turns. And because they are directions, not physical objects, they are always there, even when you can't see them. During the day, when the sun is up and the stars are hidden, the North Galactic Pole is still there, somewhere beyond the blue sky, pointing the way out of the disk. On a cloudy night, when no stars are visible, the poles are still there, steady and unchanging, anchoring the galaxy's orientation in space. The existence of these poles gives astronomers a convenient way to describe positions in the galaxy. Just as we use latitude and longitude on Earth, with the equator as the reference line and the poles as the endpoints, astronomers use galactic latitude and galactic longitude. The galactic equator is the midline of the Milky Way's disk, the great circle on the sky that traces the band of the Milky Way itself. Galactic latitude measures how far above or below that equator an object is. An object at the North Galactic Pole has a galactic latitude of 90 degrees north. An object at the South Galactic Pole has a galactic latitude of 90 degrees south. An object exactly on the galactic plane has a galactic latitude of 0. The Sun, as we discussed, is slightly above the plane, so from our perspective, the galactic equator is not quite the same as the band of the Milky Way. But the principle holds. The poles are the reference points that make the whole coordinate system work. And here's a quiet thought to hold as you rest. The stars of Coma Berenices and Sculptor are not special in themselves. They are not the brightest stars in the sky, or the most famous. They are ordinary stars, scattered across their respective patches of the celestial sphere. It's purely by chance, by the accident of our position within the galaxy and the orientation of the galaxy's spin axis, that those particular stars happen to lie in the direction of the poles. If the galaxy were tilted differently in space, different constellations would mark the poles. But as it is, Coma Berenices and Sculptor have this quiet distinction. They are the signposts, the markers, the fixed points on the compass of the Milky Way. Let's take a moment to picture what the sky looks like from the perspective of the galactic poles. If you could stand on a planet orbiting a star that was located exactly at the North Galactic Pole, and you looked up at the night sky, what would you see? You would see the entire Milky Way spread out beneath you like a vast, flat disk. The galaxy would not appear as a band across the sky, the way it does from our position inside the disk. It would appear as a great circular plane, a glowing pinwheel stretching from horizon to horizon in every direction. You would be looking down at the galaxy from above, seeing its spiral arms, its bright center, its dust lanes and star-forming regions, all laid out before you like a map. And if you turned around and looked in the opposite direction, away from the galaxy, you would see intergalactic space, the deep dark between the galaxies, with only a few faint, distant smudges of light to break the blackness. The contrast would be striking. On one side, the full glory of the Milky Way, on the other, the quiet emptiness of the universe beyond. From our actual position inside the disk, we don't get that view. We see the galaxy edge on as a band across the sky. But we can still point to the poles. We can still find Coma Berenices and Sculptor in our star charts, and know that those directions mark the true above and below of our galactic home. And there's something comforting in that. Even though we are embedded in the disk, even though we cannot see the whole structure from the outside, we can still orient ourselves. We can still say, with confidence, that way is north, out of the galaxy. That way is south, out of the galaxy. The poles give us a fixed reference, a steady compass, in a galaxy that is otherwise all motion and change. The galactic poles also connect back, in a quiet way, to the very first idea we explored tonight, that above and below are choices. The North Galactic Pole is not up in any absolute sense. It's simply the direction we have agreed to call north, based on the right-hand rule of rotation. If the galaxy spun the opposite way, north and south would swap. If we had defined our coordinate system differently, the poles might point toward different constellations entirely. The directions are real, but the labels are human. And yet, within that human framework, the poles serve a real purpose. They anchor our maps. They give us a way to talk about where things are. They are the quiet, fixed points around which the whole spinning galaxy organizes itself. And now, having named the galaxy's poles, we have completed the outward leg of our journey. We started at the sun's surface, with its physical spin poles and its magnetic flips. We stepped out to the solar system's ecliptic plane, tilted 7 degrees from the sun's equator. We stepped out again to the galaxy's vast disk, 100,000 light-years across, and we placed the sun within it, a little north of the midline, bobbing gently up and down as it orbits the center. We traced that orbit, a 250 million-year lap around a supermassive black hole, a journey we have made only 18 or 20 times since the sun was born. And now we have named the galaxy's own poles, the directions of Coma Berenices and Sculptor, the true above and below of the Milky Way. We have gone as far out as our main question requires. We have answered, as best we can, whether the sun is above or below the galaxy. It is slightly above, for now, in this moment, on its slow, bobbing journey through the disk. But our journey is not quite over. We have been looking at the large-scale structures, the orbits, the planes, the poles. Now it's time to pull the focus back inward, to the immediate space around our solar system. Because the sun and its planets are not traveling through empty space. We are embedded in a local environment, a bubble of hot gas carved out by ancient explosions, a cloud of denser material we are drifting through right now. That bubble, and the sun's own wind-blown bubble that sits inside it, are the next layers of our story. They are the closest and most intimate of our cosmic neighborhoods, and they too have their own above and below. So let's turn now, gently, from the grand scale of the galaxy, back toward the smaller, closer structures that surround us, the bubbles within bubbles that make up our immediate home in the interstellar dark. We have traveled far tonight. We have climbed from the sun's poles out to the galaxy's poles, tracing tilted planes and slow orbits and the gentle bobbing of our star through the disk. And now, having seen the largest structures, we pull the focus back inward, back to the space right around us, the local neighborhood our solar system is drifting through at this very moment. Because the space between the stars is not empty, it is filled with gas and dust, thin and scattered, but real. And our solar system is moving through that interstellar medium right now, plowing through it at 143 miles per second, while the sun's own wind pushes back against it. The result is a complex, layered set of bubbles, one inside the other, and we are at the center of the innermost one. This section is about the larger of those bubbles, the one carved out by ancient explosions, the vast, hot cavity in which our entire solar system currently sits. Let's begin with what lies between the stars. The space between stars is not a perfect vacuum. It's filled with gas, mostly hydrogen and helium, along with tiny grains of solid dust. This material is called the interstellar medium, a term that simply means the stuff between the stars. It's incredibly thin by Earth standards. The densest parts of the interstellar medium are still far emptier than the best vacuum we can create in a laboratory. But over the vast distances of the galaxy, all that thin gas adds up. It forms clouds, some of them light-years across. It collects in the spiral arms. It is the raw material from which new stars are born. And our sun, as it moves through the galaxy, passes through this medium, through regions of slightly higher or lower density, through clouds and cavities and bubbles that have been shaped by the lives and deaths of other stars. Right now, the solar system is inside a structure that astronomers call the local bubble. The name is descriptive and simple. It's a bubble, a cavity, a region of space that is much emptier and much hotter than the average interstellar medium around it. It's called local because it's the one we're in, the one that surrounds us. The local bubble is not small by human standards. It's roughly 1,000 light-years across. That's 1,000 times the distance light travels in a year, or about 6,000 trillion miles. It's a vast, irregular cavity, shaped a bit like a peanut or an hourglass, with our sun sitting somewhere inside it, not at the center, but off to one side. What makes the local bubble a bubble is that it's not just a random patch of thin gas. It's a region that has been swept clean, hollowed out by force. The leading explanation, and the one that most astronomers accept, is that the local bubble was carved by supernovae. A supernova is the explosion of a massive star at the end of its life, an event so powerful that a single dying star can briefly outshine an entire galaxy. When a star goes supernova, it blasts its outer layers into space at tremendous speeds, sending out shockwaves that sweep up the surrounding gas and push it outward, leaving behind a hot, thin cavity. Over time, if multiple supernovae go off in the same region, their overlapping shockwaves can carve out a much larger bubble, a superbubble, a vast region of hot, tenuous gas that persists for millions of years. The local bubble is thought to be just such a superbubble. The estimates for when it was formed point to a period roughly 10 to 20 million years ago, when a cluster of massive stars in our galactic neighborhood reached the ends of their lives and exploded, one after another. These explosions would have swept away most of the gas and dust that had been in the region, leaving behind a thin, hot plasma that glows faintly in X-rays. The bubble has been expanding ever since, though the expansion has slowed over time. Today, the interior of the local bubble is filled with gas, at a temperature of about 1 million degrees Celsius, which is why astronomers sometimes call it the local hot bubble. But hot is relative. The gas is so thin that if you were to stand inside it, you wouldn't feel the heat. There simply aren't enough particles to transfer thermal energy to your body. It's hot in the sense that the individual atoms are moving very fast, but cold in the sense that there are very few of them. The local bubble is a hot, empty cave in the interstellar medium, and we are inside it. Now, the local bubble is not perfectly empty. It contains a few wisps of cooler, denser gas, remnants of the material that wasn't completely swept away. And right now, the solar system is passing through one of those wisps. This smaller, denser patch of gas is called the local interstellar cloud, or sometimes the local fluff. It's a cloud of gas, mostly hydrogen and helium, that is a little cooler and a little denser than the rest of the local bubble. The local interstellar cloud is about 30 light-years across, and the Sun is currently near its inner edge, having entered it sometime in the last several tens of thousands of years, and likely to exit it within the next several tens of thousands of years. These numbers are uncertain. The exact boundaries of the cloud, its exact density and temperature and shape, are still being mapped. Different measurements give slightly different answers. The cloud may be a single, coherent structure, or it may be a collection of smaller fragments. We don't yet know for sure, and that's fine. The uncertainty is part of the quiet reality of our local neighborhood. We are still learning the layout of the rooms in our own cosmic house. What we do know is that the local interstellar cloud is moving, and the Sun is moving, and their relative motion means that we are drifting through this cloud at a gentle pace. As the Sun moves through the cloud's gas flows past us, but it doesn't touch us directly because the Sun has its own protective bubble, which we'll talk about in the next section. For now, the point is simply that we are inside a bubble within a bubble. The local bubble is the large cavity, 1,000 light-years across, carved by ancient supernovae. The local interstellar cloud is a smaller, denser patch within that cavity, about 30 light-years across, and the solar system is inside that cloud, drifting through it, carried along by the Sun's galactic orbit. Let's take a moment to picture this arrangement. Imagine a vast, dim cavern, 1,000 light-years from wall to wall, filled with a thin, hot haze. That's the local bubble. Now imagine a small, slightly denser patch of mist, drifting within that cavern, a patch about 30 light-years across. That's the local interstellar cloud. And now imagine a tiny point of light, a star with planets around it, moving through that patch of mist. That's us. We are not fixed in place, we are traveling, and our local environment changes over time as we move from one region of the galaxy to another. A few million years ago, we were in a different part of the local bubble, perhaps in a different cloud, or in the hotter, emptier part of the cavity. A few million years from now, we will have left this cloud behind and entered a new region, with a different density and temperature and composition. Our cosmic weather changes, just as Earth's weather changes, but on timescales so long that a human lifetime is just a single breath. The local bubble itself is not permanent. It is a temporary structure, a passing feature of the interstellar landscape. Over millions of years, the hot gas inside the bubble will gradually cool and mix with the surrounding medium. The bubble's walls will slow their expansion and eventually dissipate. New supernovae will go off elsewhere, carving new bubbles, and the old ones will fade. The galaxy is a dynamic place, constantly reshaped by the births and deaths of stars. The local bubble is just one of many such bubbles that exist in the Milky Way at any given time. We happen to be inside this one, during this epoch, and it has shaped the environment of our solar system for the entire history of human existence. Every human who ever lived inside the local bubble. Every star you can see with your naked eye, with a few exceptions, is inside the local bubble too. It's our immediate cosmic neighborhood, the room in the galactic house where we currently reside. And here's a quiet connection back to the earlier sections of our journey. The local bubble is not aligned with any of our reference planes in any special way. It's not aligned with the sun's equator, or the ecliptic, or the galactic plane. It's just a cavity, shaped by the random locations of supernovae that went off millions of years ago. It has no poles, no equator, no preferred direction. It's a reminder that not every structure in the universe is organized around spin axes and flat disks. Some structures are just the aftermath of explosions, the sculpted remnants of violence long past, now quiet and cooling, and slowly fading back into the general interstellar medium. The local bubble is a scar, in a sense, a healed-over wound in the galaxy's thin disk, and we are living inside it, oblivious, carried along on our slow orbit through the spiral arms. The study of the local bubble is a relatively recent development in astronomy. The bubble was first proposed in the 1970s and 80s, when X-ray telescopes began to detect a diffuse background glow that seemed to come from all directions, suggesting that we were inside a region of hot, thin gas. Since then, observations have refined the picture, mapping the bubble's shape and extent, identifying the young star clusters whose supernovae likely carved it, and tracing the wisps of denser gas that drift within it. But as with so much in astronomy, the picture is still being filled in. The exact boundaries of the bubble are fuzzy. The number and timing of the supernovae that created it are uncertain. The relationship between the local bubble and other nearby bubbles, some of which may be connected to it in a network of cavities and tunnels, is still being explored. The not knowing is, once again, part of the landscape. We are living inside a structure that we are only just beginning to see. So as you lie here, let the image of the local bubble settle around you. Picture the solar system, our small cluster of planets and moons and comets, drifting through a vast, hot cavern, 1,000 light-years wide, carved by the deaths of massive stars 10 to 20 million years ago. Picture the thinner mist of the local interstellar cloud, a patch of slightly denser gas, flowing past us as we move. And picture the sun at the center of it all, holding its planets close, pushing back against the interstellar medium with its own wind, creating a final, innermost bubble that protects us from the thin, hot gas outside. That innermost bubble, the sun's own wind-blown bubble, is the next and final structure we will visit before we drift off to sleep. It's the smallest of our bubbles, but the closest, and it has its own quiet poles, its own above and below, tied to the magnetic rhythm of the sun we explored earlier tonight. That is where we are going next, to the Heliosphere, the sun's great magnetic balloon, and the final set of poles in our journey. We have spent much of this night moving outward, from the sun's surface to the solar system's plane, from the galaxy's disk to its distant poles, from the local bubble carved by ancient supernovae to the small cloud of gas we are drifting through right now. But there is one more structure to visit, and it is the one that touches us most directly. It is the bubble the sun itself blows into space, the vast magnetic balloon that encloses all the planets, all the moons, all the asteroids and comets, everything that orbits our star. This bubble is the final layer between us and the interstellar medium, the last shield before the open galaxy, and it too has a north and a south, an above and a below, shaped by the same magnetic forces that flip and dance on the sun's surface every 11 years. The bubble begins with the solar wind. The sun is constantly shedding material, a thin stream of charged particles that flows outward in all directions. These particles are mostly electrons and protons, the stripped-down pieces of hydrogen atoms, and they stream away from the sun at speeds of hundreds of kilometers per second. This is not a gentle breeze. It's a supersonic flow of plasma, a hot, tenuous gas of electrically charged particles, and it fills the entire solar system. Every second, the sun loses about 1 million tons of material to the solar wind. That sounds like a lot, but the sun is so vast that it has been doing this for 4.5 billion years and has lost only a tiny fraction of its total mass. The solar wind is a whisper of the sun's substance, a constant outward breath that never stops. As the solar wind streams outward, it carries with it the sun's magnetic field. The magnetic field lines are frozen into the plasma, dragged along by the flow. Near the sun, the field is strong and well organized. But as the wind expands into space, the field weakens and stretches, forming a vast, spiraling pattern that fills the solar system. This is the interplanetary magnetic field, the sun's magnetic influence extended across billions of miles. And because the sun rotates, the field lines are twisted into a spiral shape, like water from a spinning sprinkler. The solar wind and the magnetic field together create a kind of inflating force, a pressure that pushes outward against whatever lies beyond. What lies beyond is the interstellar medium, the thin gas between the stars that we talked about in the last section. That gas has its own pressure, its own magnetic fields, its own flow. As the solar wind rushes outward, it eventually reaches a point where its pressure balances against the pressure of the interstellar medium. At that boundary, the solar wind slows down, piles up, and stops. The bubble defined by that boundary is called the heliosphere. The word comes from Helios, the Greek god of the sun, and sphere, a ball or bubble. The heliosphere is the region of space where the sun's influence dominates, where the solar wind flows freely, and where the sun's magnetic field is the controlling force. Outside the heliosphere lies true interstellar space, the realm of other stars and other winds. The size of the heliosphere is not perfectly known. It depends on the strength of the solar wind, which varies with the solar cycle, and on the density of the local interstellar medium, which is not perfectly uniform. But estimates place the boundary, the edge of the bubble, at roughly 100 to 120 times the distance from the Earth to the Sun. That distance, the Earth-Sun distance, is called an astronomical unit, and it's about 93 million miles. So the edge of the heliosphere is somewhere around 10 to 12 billion miles from the Sun. That's a vast distance, far beyond the orbits of the outer planets. Neptune, the most distant planet, orbits at only 30 astronomical units from the Sun. The heliosphere extends more than 3 times farther than that. It's a huge bubble, a protective cocoon that wraps around our entire planetary system. And the shape of that bubble is not a perfect sphere. As the Sun moves through the interstellar medium, traveling at about 143 miles per second on its galactic orbit, the solar wind meets resistance. The interstellar medium flows past the heliosphere, like wind flowing past a moving car. This pushes the heliosphere into a shape that has a rounded front, facing into the direction of the Sun's motion, and a trailing tail behind it. For many years, the popular image of the heliosphere was that of a comet, with a long, streaming tail extending far behind the Sun. But more recent research, including data from the Voyager spacecraft and from the Interstellar Boundary Explorer mission, has suggested a somewhat different picture. The heliosphere may be more compact, more rounded, less comet-like than once thought. Some models now suggest a shape more like a croissant or a deflated balloon, with the tail being shorter and more turbulent. The exact shape is still debated. Different models give different results, and the limited data we have from the 2 Voyager spacecraft, which are the only human-made objects to have crossed the boundary, provide only 2-point measurements, not a full map. So the true shape of the heliosphere remains, in part, a matter of ongoing research and gentle uncertainty. And that's fine. The bubble protects us, whether it's shaped like a comet or a croissant. The not knowing is just part of the quiet reality of living inside a structure we cannot easily see from the outside. Now, the heliosphere has its own internal structure, and it's worth describing it slowly because these are the layers that the Voyager spacecraft crossed, one by one, as they left the solar system behind. The innermost region, where the solar wind flows freely at supersonic speeds, is simply the heliosphere proper. As the wind moves outward, it eventually reaches a point where it begins to slow down, to feel the pressure of the interstellar medium ahead. This slowing creates a shock wave, a region where the wind abruptly decelerates from supersonic to subsonic speeds. That shock is called the termination shock. Voyager 1 crossed the termination shock in December of 2004, at a distance of about 94 astronomical units from the Sun. Voyager 2 crossed it in August of 2007, at about 84 astronomical units. The difference in distance reflects the fact that the heliosphere is not perfectly symmetric. It bulges and shifts with changes in the solar wind and the interstellar pressure. Beyond the termination shock lies a region called the heliosheath. This is a turbulent zone where the slowed solar wind piles up, compresses, and begins to turn, flowing around the obstacle of the interstellar medium. The heliosheath is a thick, churning region, and it took the Voyagers several years to cross it. Finally, at the outer edge of the heliosheath lies the ultimate boundary, the heliopause. The heliopause is the surface where the pressure of the solar wind exactly balances the pressure of the interstellar medium. It's the edge of the Sun's kingdom, the place where the solar wind stops and the interstellar wind begins. Beyond the heliopause is interstellar space, the realm of other stars. Voyager 1 crossed the heliopause on August 25, 2012, at a distance of about 121 astronomical units from the Sun. Voyager 2 crossed it on November 5, 2018, at about 119 astronomical units. Both spacecraft are now in interstellar space, still functioning, still sending back data, still drifting outward at tens of thousands of miles per hour. They are the first human-made objects to leave the heliosphere, to taste the gas between the stars, to measure the density and temperature and magnetic field of the interstellar medium directly. Their crossings confirmed that the boundary is real, that the bubble exists, and that we are, in fact, inside it. And now we come to the poles of the heliosphere, the final set of above and below in our journey. The heliosphere, like the Sun that creates it, has a magnetic structure with a north and a south. The solar wind carries the Sun's magnetic field outward, and that field has a polarity, a direction. Near the Sun's equator, the magnetic field lines are often organized into a wavy structure called the heliospheric current sheet, a vast undulating surface where the magnetic field reverses direction. Above and below this current sheet, in the higher latitudes of the heliosphere, the magnetic field has a more uniform polarity, pointing either outward or inward depending on the phase of the solar cycle. These regions are the north and south of the heliosphere, and they follow the same tilt as the Sun's magnetic poles, the poles that flip every 11 years. Recall from our earlier section on the Sun's magnetic poles that the Sun's magnetic field is not fixed. It flips polarity roughly every 11 years, part of the 22-year Hale cycle. When the Sun's magnetic north flips to south and vice versa, the entire heliosphere flips with it. The magnetic field lines that fill the bubble reverse their direction. The north region becomes south, and the south becomes north. This global magnetic reversal propagates outward through the solar system, carried by the solar wind, and it takes about a year for the flipped field to reach the outer edges of the heliosphere. The whole bubble breathes magnetically, in time with the Sun's internal dynamo. The poles of the heliosphere are not fixed points on a solid surface like the poles of Earth or the physical poles of the Sun. They are vast, diffuse regions of magnetic influence, constantly reshaped by the solar wind and the interstellar medium, and they trade places on the same 11-year beat that governs the sunspots. This means that the above and below of the heliosphere are not permanent directions. They are temporary, cyclical, part of the living magnetic rhythm of our star. Right now, the heliosphere's magnetic north points roughly in one direction. In a few years, after the next solar maximum, it will point in the opposite direction. The bubble we live inside is not static. It pulses and breathes and flips, a vast, living extension of the sun's magnetic heart, protecting us from the harder radiation and higher density gas of the interstellar medium, while itself changing shape and polarity on a human timescale. The heliosphere is the most intimate of our cosmic bubbles, the one we never leave, the one that wraps around us every moment of every day, and it carries within it the imprint of the sun's own magnetic dance. And so, as we approach the end of our journey, we have traced the full set of nested aboves and belows. The sun's physical poles steady and spinning, the sun's magnetic poles flipping on an 11-year rhythm, the tilted plane of the solar system cocked at 7 degrees to the sun's equator, the vast flat disk of the galaxy, with the sun bobbing gently above its midline, the galaxy's own poles, pointing toward Coma Berenices and Sculptor, the fixed anchor points of the Milky Way's spin, the local bubble, carved by ancient supernovae, 1,000 light-years across, with no poles of its own. And now the heliosphere, the sun's wind-blown bubble, with its own magnetic north and south, pulsing and flipping in time with the solar cycle. All these layers, all these reference planes, all these chosen directions, nested within each other like a set of quiet, invisible spheres, and at the center of them all, a small yellow star, and around it, a small blue planet, and on that planet, you, lying here in the dark, drifting towards sleep. That is where we will end, in the final section, gathering all these images together and letting them settle, like sand sinking to the bottom of a still pond, as the night draws softly to a close. We have traveled a long way together tonight, though you haven't moved from where you lie. We began with a simple question: is the sun above or below the galaxy? And we let it unfurl into a journey through layers of reference planes and spinning bodies, and vast, quiet bubbles of gas and magnetic fields. Now, in this final stretch, we're not going to introduce any new facts or new structures. We're simply going to retrace the path we took, slowly, gently, letting each image rise up one more time and then drift away, the way thoughts do in the last moments before sleep. There's nothing to remember. There's no test. This is just a soft walk back through the landscape we've explored, a chance to let it all settle into something calm and whole. We started with the closest fire, the sun. We pictured its physical poles, the two quiet points where its axis of rotation meets its glowing surface. The sun spins just as Earth does, and that spin gives it a north and a south. But the sun is not solid, and its equator spins faster than its poles, a gentle differential rotation that winds up the magnetic fields deep inside. That axis is tilted by about 7¼ degrees relative to the plane of Earth's orbit, so we always see the sun's poles at a slant, never straight on, unless we send a spacecraft like Ulysses or Solar Orbiter to fly over them and look down. Those poles are real, fixed, steady, the geographic anchors of our star. Then we turn to the sun's other poles, the magnetic ones, and we learn that they do not stay put, they flip. Every 11 years or so, the sun's magnetic north becomes south, and its magnetic south becomes north, part of a 22-year cycle that is tied to the coming and going of sunspots, those dark, cool patches on the solar surface. The exact mechanism that drives the flip is still not fully understood. The timing is observed, the pattern is clear, but the deep internal mechanics remain a matter of quiet scientific discussion, and that not knowing is part of the calm. The sun keeps some of its secrets, and we can simply let it do what it does, flipping its poles on a rhythm that has been beating for billions of years. From there, we widened the frame. We looked at the solar system as a whole, the flat plane of the planets, called the ecliptic. All the planets orbit in roughly that same plane, a relic of the spinning disk of gas and dust from which they formed. But the Sun's own equator is tilted by about 7 degrees relative to that plane, so above the Sun and above the solar system are not quite the same direction. They point to slightly different patches of sky. It's a small angle, but a real one, a quiet, geometric fact that reminds us that every reference plane is a choice. The universe does not hand us a single, universal up. We bring the labels, and we decide which plane to use. Then we took the big step. We zoomed out from the solar system to the galaxy, the Milky Way, a vast spinning disk of stars about 100,000 light-years across. We saw that the galaxy has layers, a thin disk where new stars are born, a thicker disk of older stars above and below it, and a spherical halo of ancient clusters and dark matter surrounding the whole thing. The galaxy's flat plane, the galactic plane, became our new reference, and we asked the night's central question, where, relative to that plane, does our Sun sit? The answer, as best as we can measure it, is that the Sun is currently a little bit above the galactic midplane. The exact number is uncertain, somewhere in the range of about 20 to 70 light-years north of the midline. Different studies give different answers, and the uncertainty itself is part of the honest picture. But the general point is agreed upon. The Sun is close to the plane, well within the thin disk, riding near the middle of the galaxy's stellar thickness. If the disk were a coin, the Sun would be about a hair's width off dead center. Right now, in this moment of cosmic time, we are slightly above the galaxy's midline, but we don't stay there. The Sun does not sit still relative to the disk. It bobs up and down, rising above the plane and then sinking below it, in a slow, gentle oscillation that takes roughly 30 million years for a full cycle. The amplitude of that bobbing is uncertain, somewhere between about 100 and 300 light-years above and below the plane. And as we noted, some researchers have wondered whether these disk crossings might correlate with patterns in Earth's deep history, but that link is speculative, not proven. The bobbing itself is beautiful enough on its own. It's the slow breathing of our star through the galaxy, a rhythm that has repeated about 150 times since the Sun was born. And while the Sun bobs up and down, it is also moving forward, orbiting the entire galactic center. One full orbit takes roughly 220 to 250 million years, a span sometimes called a galactic year or a cosmic year. The Sun travels at about 143 miles every second around the galactic center, and yet the orbit is so vast that we have completed only somewhere around 18 to 20 laps in the Sun's entire 4.5 billion-year lifetime. We are not old, in galactic terms. We are still making our early circuits, still tracing our patient loop through the spiral arms, carrying the planets and the moons and all of us along for the ride. Then we named the galaxy's own poles. Just as the Sun has a north and south, the entire Milky Way has 2 poles, the points where its spin axis meets the sky. The north galactic pole points toward the constellation Coma Berenices. The south galactic pole points toward the constellation Sculptor. These are the fixed reference points for the whole galaxy, the true above and below of the Milky Way. They are not physical objects, but directions, anchor points on the celestial sphere that astronomers use to map the positions of stars and gas. They remind us that even the galaxy, for all its vastness, is just another spinning body, and we can label its poles just as we label the Sun's. Then we pulled the focus back inward, away from the grand scale of the galaxy, and looked at the immediate space around our solar system. We found ourselves inside a vast, hot cavity called the local bubble, about 1,000 light-years across, carved out by ancient supernova explosions some 10 to 20 million years ago. Within that bubble, we are passing through a smaller, denser patch of gas called the local interstellar cloud. The exact boundaries of these structures and how long we will remain inside them are uncertain. We are still mapping the rooms of our own cosmic house. but we know that we are drifting, that our local environment changes over millions of years, and that the bubble we live in is a temporary feature, a passing scar from the deaths of massive stars. And finally, we visited the closest and most intimate of our bubbles, the heliosphere, the vast magnetic balloon blown by the sun's own wind. The solar wind streams outward in all directions, inflating a bubble that protects us from the interstellar medium. That bubble is pushed into a shape with a rounded front and a trailing tail by the sun's motion through the galaxy, though the exact shape is still debated. The heliosphere has its own magnetic north and south, tied to the sun's magnetic poles, and those poles flip along with the sun's every 11 years. The Voyager spacecraft crossed the outer edge of this bubble, the heliopause, in 2012 and 2018, becoming the first human-made objects to enter interstellar space. They are out there now, still sending back data, still drifting farther from home with each passing year. So that is the full path we walked tonight. From the sun's physical poles to its magnetic poles, to the tilted plane of the solar system, to the galaxy's flat disk, to the sun's position slightly above that disk, to the slow bobbing that carries us up and down, to the great orbit around the galactic center, to the galaxy's own poles in Coma Berenices and Sculptor, to the local bubble carved by supernovae, to the heliosphere and its own magnetic poles. A nested set of above and belows, each one a human choice, a reference surface drawn onto the dark, a way of orienting ourselves in a universe that has no built-in directions. And now, as we drift toward the end, let's return to the image we began with, the image of floating with no fixed floor or ceiling. Picture yourself suspended in a warm, dark sea, weightless, with no gravity tugging you in any direction. There is no up, there is no down. There are only the reference planes we choose, the poles we name, the directions we agree upon. The sun is above the galaxy if we use the galaxy's own midplane as our reference, and the right-hand rule of rotation to assign north and south. But those labels are ours. The universe does not need them. The galaxy spins, the sun bobs, the magnetic fields flip, and none of it requires our permission or our understanding. We are the ones who bring the compass. We are the ones who draw the lines. And there is something deeply peaceful in that. The universe is not demanding that we get the directions right. It is simply there, vast and old and quietly in motion, and we are a part of it, a small part, carried along on currents we can only partially map. We don't have to know exactly how far above the plane we are. We don't have to know the precise shape of the heliosphere or the exact period of the sun's vertical bobbing. The not knowing is not a flaw. It's part of the texture, part of the quiet mystery that makes it possible to lie here in the dark and feel, not lost but held. Held by gravity, by the galaxy's gentle pull, by the sun's magnetic bubble, by the thin gas of the local bubble, by the vast, slow, rhythmic motions that carry us through space without our ever feeling a thing. Let one last image settle in your mind as the night draws to a close. Picture the whole solar system, our sun and its family of planets, as a single point of light. Picture that point of light slowly rising and falling through the galaxy's disk, like a buoy on a gentle swell, like a leaf riding a barely perceptible wave. It rises above the plane, pauses, and begins to drift back down. It crosses through the midline, through the densest region of stars and gas, and continues out the other side. And then it slows, and stops, and rises again, up and down, over 30 million years, a slow, silent breath drawn and released. And all the while, it is moving forward, tracing its vast orbit around the galactic center, one lap every 250 million years. And around that point of light, the heliosphere pulses and flips, its magnetic poles trading places on an 11-year beat. And inside that bubble, on a small blue planet, life goes on, seasons turn, civilizations rise and fall, people are born and grow old, and look up at the night sky and wonder where they are. And the answer, as best as we can give it, is this. We are here. We are inside a galaxy, a little above its midline, for now. We are moving, always moving, in a dance that has no choreographer and no final curtain. And we are, in the deepest sense, at home. Let that image carry you now, softly, into whatever comes next. The night is quiet, the galaxy turns, the sun breathes its magnetic breath, and you are here, floating, held, drifting in the larger picture, with no fixed floor, and no fixed ceiling, and no need to be anywhere but where you are.